We're now in the situation where it's fairly straightforward to prove the uniqueness of prime factorizations. And the tool is going to be the prime divisor theorem and its corollary, which, as we just saw, says that if a prime divides a product of integers, then it must divide one of the integers. So let's now carefully formulate the uniqueness of prime factorizations. And we do that as follows. We assume we have a natural number n with two factorizations, p1 to a power j1 times p2 to a power j2 and so on is equal to q1 to some power k1 times q2 to some power k2 and so on. And of course, without any loss of generality, we can rearrange the factors on the left side so that p1 is the smallest, p2 is the next and so on. And similarly with the q1s, q2 and so on the right hand side. And as I note here, jm and k1 up to kn are positive integers. So the claim is that after we have rearranged this way, that p1 must equal q1, p2 must equal q2, and so on, and the number of factors on each side must be the same. More precisely, m is equal to n, p1 is equal to q1, up to pm is equal to qm, and the corresponding powers, j1 and k1, up to jm and km are the same. So that's what we're going to prove. And now, because this and these are two factorizations of the same number, and because p1 clearly divides the left side, then it must divide the right side. But if p1 divides this number here, the right side, then by what we have seen in the corollary to the prime divisor theorem, p1 must divide one of the QRs. Remember, the QRs are prime. So if you have a prime dividing another prime, the two primes must be equal. So that means that p1 must equal one of the primes on the right side. In other words, p1 must equal one of the q's. So now we can just cancel p1 from both sides, and we have one less factor on each side. And now we can just repeat the argument. We can first of all cancel p1 j1 times, because that's the number of times it occurs on the left side. And then we can cancel p2 j2 times from here. And we can keep cancelling until we have nothing left except the number 1 on the left side. And so on the right side we must have the number 1. And so that means that we must have had the same number of p1s on both sides of this equation, the same number of p2s on both sides, and so on, and then there are no further primes on either side, and so that completes the proof.